Okay, so this is going to be our first video for our liquids portion. This is a unit all about states of matter, solids, liquids, and gases. We'll start off with liquids, and then we'll move into solids, and then we'll finally finish up with gases. So as far as liquids, this presentation that I'm about to show you is easily one of the most important ones in the entire school year. So you might remember from your summer assignment that I did actually have a small segment of that that was dedicated to getting a little bit of a head start on intermolecular forces. So you may at this point even want to take a moment and do some review of that, or go ahead and continue the rest of the video, and then at the end maybe review what you did for your summer assignment and see if you've made better sense of what intermolecular forces actually are. So as you can see here on the opening slide, it's all about explaining liquid properties. And to give us an introduction, we'll first have a definition. So these are forces of attraction between molecules. These are not to be confused with bonds. Bonds are between atoms and they hold together the structure, whereas intermolecular forces, just like the internet, they're between completely distinct molecules, just like the internet is between completely distinct computers. So there are three types of intermolecular forces that we're going to talk about. First, there is a grouping that are called van der Waals forces. You'll see this every so often, but so it's important to know it, but at the same time, the two specific types are going to be the more important ones to understand. So as a group, there are two intermolecular forces that are considered van der Waals forces. Van der Waals forces are considered weak intermolecular forces, much weaker than one of the ones that we'll talk about. So your first van der Waals force, and it is actually the weakest, is called London dispersion force. Sometimes I will abbreviate that LD forces. So London dispersion forces, that's really the phrasing that you should recognize, weakest. We also have something called dipole-dipole, which is kind of an in-the-middle sort of force. It's a little bit stronger than the London dispersion, but not quite as strong as the third one. And the third one is not considered as a category of van der Waals force because it's not weak. It's actually quite strong, and it's called hydrogen bonding. So I have them in order on the slide from weakest to strongest, and that's really the first thing that you're going to want to understand. So we're going to take a little moment and we'll talk about each of the three and make sure that you understand how to determine when a molecule would have these different forces at work. So we'll start with London dispersion forces first. There is a little theory behind it, theory in terms of what electrons are doing. So electrons are in constant, they're in random motion, and the motion of one's atoms depends on a lot of different factors, but it really does come down to the way that atoms kind of work together. One atom's electrons will affect the motion of another atom's electrons. So if you take two atoms and draw them closer to each other, the electrons will begin to repel each other a little bit. Again, that's called electron repulsion. And so if you think about how one atom could be impacted by other things around it, and if you would imagine that you sort of snap your fingers. Did you hear that? That was a terrible snap. But you snap your fingers and you just stop the electron motion in an atom. If you do that at any one given moment that you snap your fingers, there is a possibility that more electrons could favor one side of the atom over the other. It's just simply chance, the way that you stop those in random motion, and you could end up with more on one side than the other, right? Well, this results in what's called an instantaneous dipole. It doesn't last very long, hence the word instantaneous, but in that instant, if there are more electrons on one side and fewer on the other side, you're creating a negative side and a positive side. If you would please open your textbook to page 455 and take a look at figure 10.5, and I think you'll start to see a visualization of what I'm talking about in terms of at any one given moment, electrons could be favoring one side versus the other, creating an instantaneous dipole. So please pause the video. Okay, so now that you've seen a little bit of a picture involved with that, we'll continue on. So this is the theory behind it. As a definition, It's considered a weak attractive force between molecules, and it results from exactly what we were just talking about, these small instantaneous dipoles that occur due to electron motion. The force will tend to increase with increasing molecular weight. That's because if you get more molecular weight, it means you have more protons, and if you have more protons, then you got to have more electrons, and if there's more electrons moving and interacting and really getting themselves all kind of riled up, you have a better chance of having more electrons on one side than the other. So understand, to say that hydrogen gas would have less London dispersion forces than chlorine gas, to give an explanation and say, well, it's because chlorine has a higher molecular mass. You will never get points for that because it's not enough. You would have to say it has a higher molar mass, which means that there are more electrons moving around, and hence, and this is the really important part, they are more polarizable. That word, polarizable, is probably top 3 words you have to know and be able to utilize in your writing in AP Chemistry. Larger atoms are said to be more polarizable. Electron cloud is easily distorted to give partial negatives and partial positive ends. So polarizable, the ability to form a pole, and we're talking poles in chemistry, we're talking about positives and negatives. So the larger the atom, or the larger even the molecule is, the more polarizable it will be, hence the stronger the London dispersion forces will be. So if you take another look at it, to continue on with London dispersion forces, excuse me, the trend that we just were talking about, where London dispersion forces increase as molecular weight increases, as I say here, it's just an approximation. In fact, molecules that have even the same molecular weight could have very, very different London dispersion forces, and it all comes down to what is known as compactness. So let me give you some pictures. So you can see in these 3 pictures, right, that you've got pentane on the left side, you have isopentane in the middle, and then neopentane on the far side. If you take a moment and count, you will see that all 3 of these have 5 carbons, 12 hydrogens. It's just in a completely different organizational pattern. And so based on what I said up top, there's a compactness issue. Do you see that pentane is the most spread out? And do you agree that neopentane would be actually the most compact because the atoms are actually in closer proximity together instead of strung out in this pentane molecule? So when you are more spread out, think about how in the pentane, the electrons are really all around. And this is a pretty large area of space. And what could happen is you could get all the electrons over on this side for just a short period of time. And then this is a very, very positive end. Where over here, the least London dispersion forces would happen in the most compact molecule, because the smaller you are, the less space you have for these electrons to really get to one side or the other side, right? If it's a really small area, there aren't really sides anymore. So the smaller you are, the less London dispersion forces you would actually have. So that's an important thing, especially as you would move into homework. Think about this, that molecule compactness is sort of the secondary thing to look at if molecular weights are the same. Okay, so that's pretty much the whole story there with London dispersion forces. As we continue on, we'll talk about dipole-dipole and then hydrogen bonding, and then I will summarize at the end and kind of give you the full rundown. So next is dipole-dipole. Okay, so dipole-dipole forces, to give you a definition, it is basically you have to have a polar molecule. So if you have 2 polar molecules, they align themselves so that the positives and the negatives all line up like magnets. So here's 2 hydrogen fluoride molecules, also known as hydrofluoric acid. The fluorine, again, is top of the scale, 4.0 for the Pauling electronegativity scale, and a hydrogen is a 2.1. They have a very, very different electronegativity value, and that's going to lead to both of these molecules will be polar molecules with the partial negative on the fluorine and the partial positive on the hydrogen. Well, you can see the way that I've drawn them in here is that the fluorine of the molecule on the left and the hydrogen of the molecule on the right are facing each other, and that will lead to an attraction that can happen, and that is a dipole-dipole. So if you have 2 polar molecules, or many polar molecules all in the same vicinity, they will align themselves within a liquid or a solid or a gas phase so that these positives and negatives, partial positives and negatives, that is, will align to line up, and that's dipole-dipole. So that one's pretty straightforward definition with that one. And then we're going to be on to hydrogen bonding. So with hydrogen bonding, the thing that I want to point out is first maybe something that doesn't seem normal. I have on the left fluoromethane. It's called fluoromethane because you can see that a hydrogen is replaced with a fluorine, and that is, instead of being just methane, fluoromethane. You can see on the right side I have a chemical that's called methanol, which is a single carbon alcohol. The OH that you see hanging off of the end, that's what makes this actually an alcohol molecule. So I say in the bullet point, both have about the same molecular weight, and they have the same approximate dipole moment, but they have a very different boiling point. In fact, that boiling point, it's not just very different, it's like significantly different. I don't actually have those values for you, but it is significantly different. And my question for you is why? Well, we're on a slide about hydrogen bonding, so that should probably be the answer. This is due to the OH group. The methanol molecule is capable of hydrogen bonding. The fluoromethane is not. So even though they both are polar molecules, the OH part of the methanol molecule is a significant impact on the overall structure and then hence behavior of this molecule in relation to other molecules. So we'll continue on and I'll give you some definitions. So the actual definition of hydrogen bonding, it is considered still a weak to moderately weak attractive force because, again, it's not a bond. It's not a real bond. Don't be misled by the phrasing hydrogen bonding to think that it's a real bond. The only types of real bonds are covalent, ionic, and metallic. Hydrogen bonding is an intermolecular force that occurs between molecules, not within them. So a weak to moderate attractive force that exists between a hydrogen atom, which is covalently bonded to a highly electronegative atom, and another electronegative atom's lone pair. Like, I know it's dicey, so here's a picture. So we have hydrogen, so let's see, which is covalently bonded to exists between a hydrogen atom, so here's your hydrogen atom, which is covalently bonded, so see the covalent bond right here, to a highly electronegative atom, that would have to be X, and another electronegative atom's lone electron pair. So this Y would need to have, it would also need to be a highly electronegative atom, but it would have an electron pair on it, would have the partial positive, and then the electron pair would have that partial negative. The thing to really note here in yellow, X and Y, these highly electronegative atoms, are usually fluorine, oxygen, or nitrogen. These are the ones that you do have to memorize. Fluorine connected to a hydrogen, oxygen connected to a hydrogen, or nitrogen connected to a hydrogen. These will hydrogen bond with other things around it. Boiling points will increase with molecular weight, and that is, again, because of what we talked about before. If you're larger, you will have more London dispersion forces. Plus, if you just think about something that's bigger trying to escape from a liquid and boil and become a gas, like the bigger you are, the harder it is to kind of get you up and moving. But if you compare just two things that have differing molecular weights and their boiling points, and then if you compare two things that have differing molecular weights plus one has hydrogen bonding and one does not, that's when this yellow statement is true. But when hydrogen bonding is present, the boiling point changes dramatically. And you will see coming up here a couple of activities that deal with this and really show this very, very well. Again, this is because hydrogen bonds hold molecules together. They hold molecules together very well. It's like super duper Velcro between molecules. And so boiling point will increase dramatically without consideration for molecular weight. That means that you could have a low molecular weight, like methanol, for instance, and you could still have a way higher boiling point than something of a much larger molecular weight. So hydrogen bonding trumps almost everything. It's super duper strong, and it's a really important thing to consider. And then again, here at the bottom in the green, what I've already mentioned. Hydrogen bond in quotation marks, not a real bond. It's just a molecular attraction. Do not be fooled. Well, what I'd like to do on the next slide is show you what it looks like. Hydrogen bonding. So water is a typical one that will hydrogen bond and one that you definitely want to know about. And do you notice here that I have several water molecules? Now notice please, I'm not showing the extra electron pairs that would be attached to oxygen, but you still have your bent configuration and your water molecule. And what do you think the green dotted arrowy lines in the middle might mean? Hydrogen bonding, perhaps? Why, yes. Now please note, a drawing like this is something that you may actually need to draw at a certain point, because to understand how hydrogen bonding works means that you understand that the bond is happening between a negative portion of one molecule and a positive portion of a second molecule. So please take a moment and really let that sink in. It's the negative portion of one molecule that will attract the positive portion of a second molecule, and then this network is formed from that. Okay, so to summarize, come on, baby. There we go. Okay, to summarize. Sorry, wasn't going for some reason. So how to determine that an intermolecular force is at work in a molecule. So we're going to review everything, plus you're going to actually see your connections that are going to help you with your homework. So first off, you want to always look at the molecule. You would have to have a Lewis structure or some sort of at least idea of electronegativity or molecular geometry in your head. If you can't draw Lewis structures and if you don't know molecular geometries, you are going to struggle with this part immensely. So again, it is supposed to be progressive here. You got to know some stuff. So first thing, if you determine that a molecule is nonpolar, London dispersion forces are the only thing that's going to be there. London dispersion forces occur in every molecule on the face of this planet, and I guess any other planet also. So if it's nonpolar, London dispersion forces only are at work. If you have a higher molar mass, you would have more London dispersion forces, lower molar mass, less dispersion forces. If you are a polar molecule, you will have London dispersion forces because you are a molecule, and all molecules have London dispersion forces. But if you're polar, in addition, you also have dipole-dipole interactions, and that's because you have those partial positives and negatives interacting between molecules, and that's going to hold them together a lot better. Now, you can be a polar molecule and still have one other step to go. So if you determine that the molecule is polar, you need to look very carefully. Does that molecule contain hydrogens that are bonded to nitrogens, oxygens, or fluorines? If that is the case, it still has London dispersion forces because all molecules have London dispersion forces. It will have dipole-dipole interactions because, after all, this is a polar molecule. And finally, it will, of course, have hydrogen bonding because of the hydrogen bonded to a nitrogen, oxygen, or fluorine. So it's like a progressive kind of a list. When you're looking and comparing between molecules, first determine polar or nonpolar. After you determine that, if it's a polar molecule, then double check for hydrogen bonding possibilities, and then you're adding on as you go, okay? So record any questions you have, bring them back to class, and we'll talk tomorrow. See you later.